Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the channel Chandan Physics. In this video, we are going to discuss applications of uncertainty principle. Three applications. 1. Ground state energy of harmonic oscillator. 2. Ground state energy of hydrogen atom. 3. Non-existence of electrons inside nucleus. Let's begin. By using uncertainty principle, we can calculate what be the ground state energy of harmonic oscillator. First, we have to consider a particle, that particle of mass small m, and that particle executing simple harmonic motion SHM with a angular frequency of omega, and the displacement of such particle from that of mean position is small x. Here kinetic energy, that is half m v square. V be the velocity of such particle, velocity of that particle, the particle having the mass small m, its velocity. In terms of momentum, we just multiply m and divide m, so it will be p square divided by 2m, whereas p the momentum. Equation 1. And potential energy, which is half m omega square x square. This is the potential energy of that harmonic oscillator. Therefore, total energy is equal to kinetic energy plus potential energy. The total energy is equal to kinetic energy p square divided by 2m, potential energy half m omega square x square. Equation number 3. We have to calculate the ground state energy, that is the minimum energy of harmonic oscillator, by using uncertainty principle. When we are dealing with that uncertainty principle, that is uncertainty in position and uncertainty in uncertainty in momentum. In that of energy expression, here is momentum term, that is the position term. Therefore, we can write using uncertainty relation, that is uncertainty in position into uncertainty in momentum, that momentum also along the direction of that position is greater than equal to s square by 2, or for our convenient we use del x into del p is equal to s square by 2. In that of situation, the uncertainty in position is equal to x, that is the uncertainty in that of position, as that particle displacement of that particle from the mean position is x. So, uncertainty in position B x and uncertainty in momentum as p. Therefore, x into p is equal to h cut by 2. From that relation, we can write p is equal to h cut divided by 2x, equation number 4. Now, we can put the value of p in that of equation number 3. Putting the value of p in equation 3, we get the energy expression E is equal to, in place of p, that is h cut by 2x whole square divided by 2m plus half m omega square x square, or E is equal to h cut square divided by 4x square divided by 2, that one as 8 m x square plus half m omega square x square, equation number 5. Our aim is to calculate ground state energy, means the minimum energy for that of harmonic oscillator. The energy should be minimum. The condition is that we have to differentiate that energy expression with respect to x and equate it to 0. E will be minimum for those value of x for which its differentiation, that is dE with respect to that x is equal to 0. So, d by dx, that is h cut square 8 m x square plus half m omega square x square is equal to 0. Differentiation of that term as write h cut square 8 m 1 divided by x square, that is minus 2 divided by x cube plus half m omega square, differentiation of x square with respect to dx, that is 2x is equal to 0, or 2 8 minus h cut square divided by 4 m x cube plus 2 to cancel out m omega square x is equal to 0, or m omega square x is equal to that value minus h cut square divided by 4 m x cube So, that x is multiplied here, or we can say that x is multiplied here, then we have x to the power 4th is equal to minus h cut square divided by that m omega square, this value as 4 m square omega square, that is not minus, in that side it will be plus. So, the value of x square under root, that is h cut divided by 2 m omega, that equation number 6. Therefore, equation 5 becomes for that of minimum value. Therefore, equation 5 will be, that is the E minimum h cut square divided by 8 m, in place of x square we substitute that value, h cut 2 m omega, h cut divided by 2 m omega plus half m omega square, again in place of x square, that value as h cut divided by 2 m omega, h cut divided by 2 m omega. Now simplifying it, 2 m omega to that of numerator side, 1 m cancel out, 1 h cut cancel out, 2 8, that is 4, that value as h cut omega divided by 4 plus that value again same, h cut omega divided by 4, 2 to 4, 1 m cancel out, omega square, omega as omega, that is the E minimum, or E minimum is equal to 2 times h cut omega divided by 4, which is equal to h cut omega divided by 2, that is 1 by 2, in place of h cut, that is h by 2 pi, in place of omega it is 2 pi nu. This is the value of E minimum. Here we substitute h cut is equal to h by 2 pi and angular frequency omega is equal to 2 pi nu. That substitution is used here. Therefore, E minimum is equal to 1 2 to cancel out, pi cancel out, that is half h nu. This is the ground state energy of harmonic oscillator. This is the expression for the ground state energy, or we can say minimum energy of harmonic oscillator. This is the expression for ground state energy or minimum energy of harmonic oscillator. It is also called zero point energy. The ground state energy of that harmonic oscillator is also called 0 point energy. The name says 0 point, but actually that energy is not 0. That is the non-zero energy, which is the minimum energy for that of harmonic oscillator, which is equal to half h nu. So here, by using the uncertainty relation, Heisenberg's uncertainty relation, we calculate the ground state energy of harmonic oscillator. We consider a particle having mass m with a simple harmonic motion of angular frequency omega, and displacement of that particle to that mean position is x. The total energy for uncertainty relation, uncertainty in position and uncertainty in momentum is used, and the energy to be minimum is differentiation equate to that of 0 condition for x square, and that the value is put in that of energy expression, and we obtain the minimum energy for that of harmonic oscillator, which is called the 0 point energy. Next application, we have to calculate the ground state energy of hydrogen atom. Let us consider an electron which revolve around that of nucleus of a hydrogen atom in an orbit of radius r. If we prefer that is the nucleus, an electron revolve around that of nucleus with the radius r. In that of hydrogen atom, there are a number of orbits through which electron revolve, but n is equal to 1, n is equal to 2, n is equal to 3, like this. N is equal to 1, that is the ground state. The electron when revolve around that of nucleus at that of radius, whereas that n is equal to 1, we call it as ground state, and the energy possessed by that of electron in that of ground state we call the ground state energy of hydrogen atom. In that session we discuss what be the ground state energy of that hydrogen atom by using Heisenberg's uncertainty relation. First we have to calculate its potential energy, kinetic energy and total energy. Here kinetic energy, that is half mass of electron and the velocity at which that electron revolve around that of nucleus. Again it in terms of momentum, that is p square divided by 2m, that is equation number 1, and its potential energy as minus a constant and z is the atomic number, E square divided by r, with the distance. For hydrogen atom, z is equal to 1 and that constant value k is equal to 1 by 4 pi epsilon naught. Therefore, potential energy minus k E square by r, equation number 2. The total energy of hydrogen atom, that is the kinetic energy plus potential energy. E is equal to kinetic energy p square by 2m minus potential energy k E square by r, equation number 3. We can use the uncertainty relation. Using uncertainty relation, uncertainty in position into uncertainty in momentum greater than or equal to h cut by 2. Here we prefer del x to del p is equal to h cut. Why we use h cut? For our convenient. From that of uncertainty relation, uncertainty in position into uncertainty in momentum greater than or equal to h cut by 2, either it is equal or greater than of that value. Here h cut which is greater than that of h cut by 2. So, So, we can use it, no objection is here. And in that of situation, uncertainty in position is equal to the radius r, and uncertainty in momentum is equal to p. Therefore, r into p is equal to h cut. So, p in terms of r as h cut divided by r. Therefore, equation 3 becomes in place of p we substitute h cut by r. E is equal to h cut by r whole square divided by 2m minus k e square divided by r, or E is equal to h cut square divided by 2m r square minus k e square divided by r. Let equation number 5, or the condition is that to calculate the ground state energy, we have to differentiate that energy with respect to r and equate to 0. E will be minimum, for those value of r for which dE by dr is equal to 0. So, d by dr h cut square 2m r square minus k e square divided by r is equal to 0, or its differentiation result as h cut square divided by 2m, that is the constant term, 1 by r square minus 2 divided by r cube minus k into e square, then 1 by r, that is minus 1 divided by r square is equal to 0, or 2 cancelled out, minus h cut square m r cube minus plus k e square divided by r square is equal to 0, that term to this side. So, k e square divided by r square is equal to h cut square m r cube, or 1 r, here 1 r cancelled out, we have k e square is equal to h cut square divided by m r. Our requirement is r, so r is equal to h cut square divided by k m e square, Look here, h cut constant, k constant, m constant, means the value of mass of electron we know, then the charge of electron. So, all these terms are constant. So, r is a constant value. Now, that value of r, when we put in that of energy expression, then we obtain the minimum energy. We write here, putting the value of r, therefore, equation 5 will be E will be minimum when we put the value of r here. So, h cut square divided by 2m, in place of r we substitute these values, that is h cut square divided by k m e square whole square minus k e square divided by, in place of r again we substitute h square divided by k m e to the power square. Now simplifying it, we have E minimum is equal to that is squaring term to this side. Here we have k square m e to the power 4th divided by 2 h square minus again k square m e to the power 4th divided by h square, since e square e to the power 4th k square, or E minimum is equal to, look that equation, that is half k square m e to the power 4th divided by h square minus k square m e to the power 4th divided by h square, half this minus this one, that value will be minus k square m e to the power 4th divided by h square. The value of k known to us, value of m, e, h, we known these values. We know that the value of k as 1 by 4 pi epsilon naught, that value as 9 into 10 to the power 9, the unit Newton meter coulomb minus 2, and the value of mass of electron 9.1 into 10 to the power minus 31 kg. Charge of electron 1.6 into 10 to the power minus 19 coulomb, and h with the Planck's constant, here h is equal to h by 2 pi, and the value of h 6.625 into 10 to the power minus 34 joule second. So E minimum is equal to minus 13.6 electrovolt. When we put all these constant values in that of expression, we finally obtain E minimum is equal to that one. This is the ground state energy of hydrogen atom. Ground state energy of hydrogen atom. So here we easily calculate the ground state energy of hydrogen atom by using Hagen-Bosch uncertainty relation, first using that condition and finally the value. Next application, non-existence of electron inside the nucleus. We know that the size of nucleus is of the order 10 to the power minus 14 meter. If the electron is confined inside the nucleus, then the uncertainty in that position cannot be greater than to that order. Here we can say the uncertainty in position is nearly equal to that value 10 to the power minus 14 meter. Using the relation del x del p greater than equal to h square by 2, that is del x del p is equal to h square by 2. So del p is equal to h square divided by 2 into del x. So h square h by 2 pi is the uncertainty in position, the constant values are putted, and we obtain del p is equal to that value, which is the uncertainty in momentum, means that is the momentum of electron inside that of nucleus. Now the energy of that of electron inside that of nucleus we can calculate by using that relation, This is the relativistic expression for energy. E is equal to p square c square plus m naught square c to the power 4 under root. Since that value is very less than this value, so it can be neglected. Here we can say m naught is the rest mass of electron, c the velocity of light. So, E is equal to p c. So, value of momentum and c is putted, uncertainty in momentum is equal to that momentum of electron inside that of nucleus in terms of joule. When we convert that joule to that of electrovolt, divide 1.6 10 to the 19 coulomb, finally we obtain E, which is nearly equal to 10 mega electrovolt. That is the energy required to place electron inside that of nucleus. This means that the electrons exist inside the nucleus, their energy must be of that of order 10 to the power 6, 10 into that is the order of 10 mega electrovolt. But experimentally it is shown that in that of beta decay, the energy of electron only this range 3 to 4 mega electrovolt. So, it can be conclude electron cannot exist in that of nucleus. So, here with the help of this video lecture we understand applications of uncertainty principle. First we calculate ground state energy of harmonic oscillator. This is the ground state energy half S nu, which is also called 0 point energy. Next, ground state energy of hydrogen atom. This is the ground state energy of hydrogen atom expression. All the constant values are putted and we obtain minus 13.6 electrovolt. Next, why electron not exist in that of nucleus? By using uncertainty relation, we conclude that energy required 10 mega electrovolt, but electron have the energy this range. So, we can say that electron can't exist in that of nucleus. So, with this useful and informative notes, let me wind up the session. Thank you.